This is Coronado on behalf of JCSC, and this is our next session of Bridging the Gap. So for those of you who aren't familiar with our sessions of Bridging the Gap, I invite you to take a look at the introduction at our YouTube channel, and that'll give you a more robust explanation of kind of what we do, what we're doing here with these sessions. You can see a little bit of that right here, but you get a more detailed explanation if you jump on our introduction. So with that said, let me clear the screen here. We're going to jump into the current session, which is entitled W6-2 to Shear Panel Detail. And what we're trying to do here is identify the critical pier. So the question is, how do we use judgment to identify the critical pier in a lumber framed shear wall system? So let me see, with that, let's see if we can scroll down. And so here we have a partial roof plan, all right? And I can even zoom in a little bit, I think. Okay, so this is a partial roof plan. And in particular, what we're gonna look at is this shear wall. So this would be the exterior wall. And I believe this is the north side of this structure. So this is the north wall, the north exterior wall. All right, so if we look at this, we see that we have headers here. If you're not familiar with a header, I believe that's covered in another Bridging the Gap session, but think of these as openings. These are openings in the wall. So really what we're left with is shear walls, a shear wall that has a pier here, a pier here, 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 and here. All right, so in theory, we have 1, 2, 3, we have 5 piers in this wall. All right, what we would call piers in the overall shear wall system, or also known as a shear wall line. Okay, so this whole thing across here would be a shear wall line, and these are the 5 piers in the shear wall line. All right, so with that said, in an ideal world, we would conduct all kinds of numerical analysis on this. And in particular, what we're trying to get to is the design of our uplift. Okay, we want to determine what is the critical uplift in any one of these shear wall piers. So in an ideal world, sure, we'd run all kinds of analysis, all kinds of numbers, all kinds of stresses on each one of these piers, rocking back and forth, right? Because let me see if I can draw here. In theory, if this is, let's say the slab on grade, and we have a shear wall pier here, and I'm just looking at one particular pier, in theory, we have a rocking force on that pier, right? If it's resisting an earthquake, it's going to be going back and forth. If it's resisting a lateral pressure, such as a wind force, then it'll be in one direction or the other. But eventually, it needs to be able to resist that uplift at both corners, right? Here and here. Okay, so yes, if we had all the time in the world and all the budget in the world, absolutely, that's what we would do. But that's not reality, right? That's, again, one of those that maybe that's what we do in school, but in practice, we just don't have time for that. That's not reality. So what we need to do is look at it, and by observation, we need to be able to determine which one is going to be the critical pier. And then once we determine what the uplift is for the critical pier, meaning which one is going to have the greatest amount of uplift, then more than likely what we're going to do is design all of the ends of the piers for that uplift. Okay, does that make sense? So whatever this magnitude of net uplift is, that's how we're going to connect. That's in theory how we would connect that end, that end, that end, that end, and so forth. We would all connect all the ends of the piers in the same manner. That's more than likely how you would need to do this in practice. Okay, let me clear the screen. So now let's look at our individual piers. So first we have a pier here on the left side, and we can call this Pier 1. I know that you don't have dimensions in this plan, but the building codes do establish a minimum width of pier that you can have. Actually, it doesn't specify a minimum width. What it does is specify a minimum aspect ratio. Okay, so if your pier is too narrow to meet that aspect ratio, then it doesn't qualify as a pier. And the reason for that is because it would be deemed to be too flexible. So if we were to have a pier, and let's say we have, one pier here, and then the next pier over is something like this. The idea is that because of the stiffness of one pier versus the other, um, the vast majority of the force would go into this pier. This pier here, this pier would be deemed to be too flexible, too narrow, too flexible, and hence we would take this out of the evaluation, the evaluation, and throw 100% of the load into this pier. Okay, so the code does not allow us to use piers that are excessively slender. And that is a topic that's covered in another Bridging the Gap session. So you'd have to find the one with the aspect ratio for that. Let's move on, clear the screen here, and we'll move on and now look at the next pier over. Okay, so that would be this one. I can tell you that in general, the longer piers are not going to govern, okay? The longer piers, because they are longer, and again, if we sketch this out, if we have our slab on grade here, and then we have a pier doing this, um, and more than likely it's going to have gravity loading on it, right? Plus its own self weight, so that when there is a lateral force on this overturning force, okay, the overturning force from that lateral force that wants to rock this pier over like this is going to be counteracted by the force, by these forces, by the gravity load that's going to be pushing down on the wall, hence creates a countering, what we would call a countering moment, a counterclockwise force, if you will, that would resist the overturning from the lateral force. So the bigger the piers, the less likely that they are to be susceptible to overturning. So by inspection, we're not going to evaluate this one. I think almost by extension, I would say the same thing about this one, right? Now it looks to me like potentially what we're looking at is possibly this pier and possibly this pier as being the more critical ones. Okay, so now let's indeed look at this pier here. Now this pier, if you look at this, it has an interesting feature to it. And that is that it has, let's see if you can, give you a second here, see if you can figure it out to see what's different about this pier. Well, this pier has a wall that intersects the pier. So these two walls, in all likelihood, unless you're detailing them to be built in a certain way, which would be unusual, more than likely these two walls are connected right here. So what that does for us is if we were to look at, let's say this sketch is still the same wall that we have here, But now what we have is a wall that intersects where? Kind of like towards the end, right? Like probably around here. So that's the wall that frames into our the pier that we're evaluating. But what do you think this wall does for us, this intersecting wall does for us here? Sure, when this tries to overturn, because these are connected here, right? This wall is connected here and here. This whole wall that intersects the orthogonal wall is also going to hold down or participate in holding down our pier from uplifting. Okay, so not only do we have the dead load from the roof weight, the dead load or the weight of the wall, but we also have this orthogonal wall that kind of helps to anchor down our pier at this end so that it doesn't lift up at this end. The same is not quite true if we reverse the load, right? If we look at the force, if we look at the force when it goes in the other direction, our lateral force, let's say an earthquake force or a wind force, and it's pushing our pier from right to left, this wall isn't going to help as much. It does a little bit, but because it's skewed way over to the left end, it only is going to help us a little bit in resisting the overturning that's induced by the black force here. Okay, so so potentially that means that now we have, let me see, what do I do here? How about if I do this? Yeah, I'm going to put a little gold star there. Potentially that might be one critical end of a wall that might be most susceptible to lifting. Okay, now let's look at the last pier. Okay, let's look at the last pier, which would be then this one here. Well, by extension of what we discussed here, the same applies here. And more so, right? Because one, this wall is at the very end. So it's not even moved in a little bit. It's holding down the very end of the pier. And the wall is an exterior wall. So if the wall is an exterior wall, it's probably going to weigh even more, than an interior wall. All right. So this end here is most likely not going to be a critical uplift condition. It's not going to be our critical uplift condition. So really what we're left with then is either potentially this one here or this one here, right? Those are our two possibilities. I would say that more than likely, oh wait, there is one other thing to consider. So let me clear the screen here. Okay, so again, we're now down to two options. Remember, we're down to two options, right? That would be this one or potentially this one. Take a look at it. I'll give you a second and you tell me which one you think might be the most critical uplift condition. Tell me how you think this plays a role in what we're looking at. Those are headers, right? What's a header? Well, simplistically, if for our purposes right now, which is simply to calculate overturning, a header is a beam that supports this amount of roof, right? Supports this roof area here, is tributary to this beam. So that means that the amount of resistance that we have at this end is not only the weight of the roof over the wall plus the weight of the wall itself, but it's also the amount of roof over this beam is going to participate in keeping this end from lifting up. By extension, this beam, this header, brings in this amount of contribution from the roof to resist that uplift. Now, which one do you think is the most critical pier to evaluate? Yeah, I think I would go with this one as well. A heart. I've never used a heart. No, that's not what I meant to do. How about if we use a star? Yeah. Okay. That would be the end. If I were to look at this wall and I have to use judgment in determining which end is gonna have my greatest overturning due to lateral force, that would be the pier. That would be the end of the pier that I would evaluate, and whatever net overturning I have at this end, I would treat all of the other ends of the piers to resist that net uplift. Okay. Let me see if let me clear the screen. I think with that we've covered what we needed to cover here. Yes. So again, check out the introduction to understand better what bridging the gap sessions are. Other sessions that are related to the current session that we're just covering. Look in our channel for any W6 sessions, any sessions entitled W6. They'll have other aspects of this shear wall that we're evaluating here. We'll cover what a shear wall line is, the forces that are in the assembly, how to determine the forces in the assembly, how to determine the capacity of the elements, and designing the connections for those assemblies. So just look for other sessions that are entitled W6, and you'll find other related topics to what we just covered right now. Okay, appreciate a thumbs up from you if you enjoyed this, if this was helpful. If you hover over the JCSE logo, you can click on it and you'll be able to subscribe to our channel to stay tuned to other Bridging the Gap sessions. And that's about it. Okay, real good, guys.